So I want to do more equations. So if I give you this example, there's nothing bad about this problem. X squared plus 3x equals 10. And I'm just going to ask you to solve this by, whatever method you prefer. What would you do first? Subtract 10. X squared plus 3x minus 10 equals 0. And then you would try to do what? What would you try to do with that? Yeah, you always want to try to factor it, and this is factorable, right? Two numbers that multiply to negative 10 and add to positive 3 are 5 and negative 2. Good. So then we'll set each factor to 0, and we'll solve for x. So x equals negative 5, x equals 2. Is that okay? This is a nice, friendly problem. Now I'm going to change this problem a little bit. What if I write x to the power 4 plus 3x squared equals 10? There are similar. Go ahead. Yeah, I will still subtract 10, but what I want us to realize, although this is not a quadratic equation, it's not a second-degree equation, it's a fourth-degree equation, but it has the same pattern as the equation I just wrote. You have two variable components where one is square of another. Just like here, we have x, and if you square x, you get x squared. Over here, we have x squared, and if you square that, you get x to the power 4. It's the same quadratic pattern. You have a square term, not square term, and then a constant. You see that? It's kind of similar. So I can approach this problem in the same way. Yes, I will subtract 10 from both sides. But to make this problem look like a quadratic equation, we're going to employ this little trick we call substitution. And we use this in math a lot. It's not the same substitution we use to solve systems of equations. It's a substitution we're going to replace a more complex part of an equation with a simple variable. So we're going to solve this problem in steps. I'm going to say let u, for example, a new dummy variable, equal this term right here, equal x squared, the term that you need to square to get the other one. Because look, if I do that and I replace every x squared with u, I'll get u squared plus 3u minus 10 equals 0. See what I did? Instead of each x squared, I put a letter u. Go ahead. Well, first of all, no, this is x to the power 4, right? So, but if I square x squared, I'll get x to the power 4. Do you agree with that? So I'll just square in the u to get x to the 4. So basically, what I'm trying to do, I am replacing the term that you need to square in order to get the other term. So now this looks just like a traditional quadratic equation, right? This is a basic quadratic equation where u is the variable, and I know how to solve that, right? I can factor that. U plus 5, u minus 2 equals 0, and then I'll set both of those to 0. I'll get u equals negative 5, and u equals 2. So I'm solving an easier equation, right? This is a much easier equation than what I started with. for that newly introduced variable. So after I found that dummy variable, I can substitute back and find x. I can substitute back and find the original variable. We agreed that u was x squared, right? So instead of u, I can put x squared back in there. So it's x squared equals negative 5, x squared equals 2. And then I can solve for x. So basically what I'm doing, instead of solving one complex, difficult equation, I'm solving 3 easier ones. Right? If I gave you a choice, what would you like to have on a test? 1 really, really hard equation or 3 easier ones? 3 easier ones. And that's what we're doing here. Solving the original, and again, we can solve the original equation by brute force, but you'll see some examples where we really need to go through that substitution motion. But anyways, if I go further, this has no real solutions. X squared cannot equal negative 5, so no real solutions. Here, x equals plus or minus the square root of 2. So these are the solutions to that equation. Let me try a similar one. What if we do y to the power 6 plus 4y cubed minus 5 equals 0? This is a 6th degree equation, but it still has that same pattern as the quadratic equation. You have a constant, you have a variable, something, and if you square y cubed, you will get y to the power 6. So it has that quadratic pattern. Square, not square, constant. Do you see that? So we can make that substitution again. I can say let u equal the term that you need to square in order to get the other term. So let u equal y cubed. And then for every y cubed, I'm going to put a u. So instead of y to the power 6, I'm going to have u squared. Instead of y cubed, I'm just going to have u, and 5 is a 5. So now this is a standard quadratic equation. So this is what I mean. Instead of solving a hard one, I'm going to first solve a simpler one, right? This is a very friendly quadratic equation, right? There's factors, everything's nice and clean, right? What is it? U plus 5, u minus 1 equals 0, right? So then I'll set both of those to 0. U plus 5 equals 0, u minus 1 equals 0. So u equals negative 5, u equals 1. Is that okay? So that's solving a simple, friendly quadratic. Now the original equation was in terms of y. So I have to find y. Well, here I'm going to substitute back and solve for the original variable. So u was y cubed, so that means y cubed equals negative 5, and y cubed equals 1. So you're substituting back. So then to solve for y, you just take in the cube root, so you get a cube root of negative 5, and y equals 1 when you take the cube root. So these are the two real solutions that we get. whatever the cube root of negative 5 is. That's a real number, whatever that is. Okay? Now, a 6th degree equation, because that's what we start with, a 6th degree equation has a total of 6 solutions. And we found all real solutions. It has 2 real solutions. It has 4 funky-looking solutions. And you'll be looking for the funky ones in college algebra. Okay? But at least we got the real ones. So does that process make sense? How you replace a part in the equation with a new dummy variable? You can call whatever you want. We just called it u. And then you solve in terms of the new dummy variable. And then you go back, resubstitute, and solve for the original variable. Okay? So again, we solved 3. Here's 1, 2, 3 easy equations, instead of trying to do the original one straight on. Okay, now here's a fun equation. And this was a square root of x here. I'm going to solve this equation 2 ways. First method, treat it as the equation that has a square root. Equation with radicals. Remember how we solved that? Step 1, isolate the radical. Step 2, kill the radical. Step 3, check for more radicals. Step 4, solve whatever's left. Step 5, check your solutions. Remember that? You just did those on Monday. We kind of had that worksheet. So let's try that. So isolate the radical. I can just add that square root to the other side, right? And I'll get that radical by itself. X minus 4 equals 3 square roots of x. So that's the first step. Second step, square both sides. Again, remember, I can have a constant multiple of a square root. It will still kill the square root. So the left side is x squared minus 8x plus 16. The right side is 9x. What? Don't ask me where the 8x came from. Okay. We all know where the 8x, okay. Right? All right. So anyways, nice equation. Move 9x over. We get x squared minus 17x plus 16 equals 0. Right? I believe I can factor that. Problem's coming out pretty nice today. X minus 16, x minus 1 equals 0. So x is either 16 or x equals 1. Is that okay? Are we done? Ryan said no. What else do I need to do? What? No, you went like that. That was the correct answer. So what do I need to do? What? Yeah, you do have a clue. Yeah. Right, you have to check. Every time you square both sides, you have to check for extraneous solutions. Remember that story? Checking for extraneous solutions. So if I go back all the way to the original problem, and we're going to check x equals 1. If I plug x equals 1, I'll get 1 minus 3 times square root of 1 minus 4. Is that equal 0? I mean, this is 1 minus 3 minus 4. That's what that is. Is that equal 0? No, it does not equal 0. So x equals 1 is an extraneous solution. Remember, every time we do equations that involve square roots, when we square both sides, we have to check, because squaring both sides ignores the negative sign. When I plug in 16, we'll get what? 16 minus 3 times the square root of 16 minus 4. Is that going to equal 0? So this is 16 minus 3 times 4 minus 4. Yeah, so that's 16 minus 12 minus 4. That does equal 0, so that checks. So this is the only solution. That one is extraneous. Right? Well, that's a good review how to solve those. So we've done those for a while. We've done those a few weeks ago. Any questions on this method? When you see a square root, you isolate the square root, you square both sides, you solve, and then you go back and check. Good? All right. Now, the other method, what I notice is what happens if I square the square root? If you square the square root of x, what do you get? X. You get that, right? So it also has that quadratic pattern. You have a term that's not squared, but if you square that term, you're going to get the first term, and then you have a constant. So it follows that same pattern. If I solve this by substitution, so the method 2 here, so again, the equation was x minus 3 root x minus 4 equals 0. I'm going to use substitution. Let's call it, well, that's basically what this is called equation of quadratic type. Equation of quadratic type. And if I let u equal the square root of x, if u equals the square root of x and I replace every square root of x with u, I'll get u squared minus 3u minus 4 equals 0, right? If you square the u, you're going to get the x. So it has that same pattern. You agree with that? This is a friendly quadratic. It's very factorable. If I factor that, u minus 4, u plus 1 equals 0. Right? You set both of those to 0. U minus 4 equals 0. U plus 1 equals 0. So u equals 4. U equals negative 1. Is that okay? So that was easy to solve for u. Now we're going to substitute back. To find the original variable. So that is square root of x equals 4 and square root of x equals negative 1. Right? So the first one, if the square root of x equals 4, what is x? 16. X equals 16. Well, this one has no solution. Square root of x cannot equal negative 1. And this is that extraneous solution. But you see, I catch it really early. I don't need to solve this because that has no solutions. If I square both sides, I'll get x equals 1, right? But I knew not to do that because square root cannot equal negative number, so I'm done. No solutions here. Okay, so that, see, we catch that extraneous solution early, so we're done. That's the only solution. So actually, I don't know which one is easier. This is probably easier. When you make a substitution and you just solve it as a quadratic, you don't have to check because you catch your extraneous solutions early. Does that make sense? Okay. Here's another example. M to the power 2/3 minus 2m to the power 1/3 minus 8 equals 0. So this equation involves cube roots. The 1/3 power is a cube root. And I have two different cube roots, right? This is a cube root, and that's a square of that cube root, right? The 2/3 means you squaring the 1/3. So it's, again, it has that quadratic pattern. If I square m to the power 1/3, I will get m to the power 2/3. Right? That's the pattern. So it has that quadratic pattern, so I can let u equal m to the power 1/3. That'll be my substitution here. And then equation becomes u squared minus 2u minus 8 equals 0. Which is, again, a very friendly, normal quadratic that we can factor without any issues. Right? This factors very easily. U minus 4, u plus 2 equals 0. And then we'll set both to 0. We'll get u equals 4. And we'll get u equals negative 2. Right? So then we have to substitute back. So that means we have m to the power 1/3 equals 4. We have m to the power 1/3 equals negative 2. And in order to get rid of the power 1/3, you just cube both sides. Because again, 1/3, power 1/3 is a cube root. To kill a cube root, we'll just cube both sides. And when you cube both sides, you don't need to worry about extraneous solutions, because cubes preserve the sign. So then m equals 64, m equals negative 8. And that's it. How much sense is this making? And this is a very common practice in math. We use it in other applications where you replace a more complex part with a simple part, and then you deal with the simple part, and then you go back and finish the problem. So again, you're splitting your one messy problem into a few simpler ones, right? Let me show you an example where we can do this problem both ways. Here's an example. 3x plus 2 squared plus 7 times 3x plus 2 minus 8 equals 0. We can solve this problem with the brute force. We can open up all the parentheses, combine like terms, and then see what that leads us. It's going to be messy, okay, if I do it like that. And I'm going to do it like that, show you which kind of work we're talking about. So method 1, brute force. So open up the parentheses, we'll get 9x squared plus 12x plus 4, right? That's how you square a sum. Then it is plus 21x plus 14 minus 8 equals 0, right? Combine like terms, what do we get? 9x squared plus 35x, right? Plus 10 equals 0. We can probably factor that. Can we factor that? Two numbers that multiply to 90 and add to 35, right? This is how we do those. We multiply 9 and the 10. So the product is 90. The sum is the number in the middle. So that's a good review of factoring. Can you think of two numbers that multiply to 90 and add to 35? Two numbers that multiply to 90 and add to 35. Two numbers that multiply to 90 and add to 35. Does that even work? It should work. This problem is kind of nice. Did I make a mistake? I could have made a mistake. Oh yeah, that's 33. 12 plus 21 is 33, not 35. Come on. You should have been catching those little errors. Well, that makes it easier. Yeah, 30 and 3. Okay, so that was a trick question. So the numbers are 30 and 3, right? So then we'll solve this by factoring, by grouping 9x squared plus 30x plus 3x plus 10 equals 0. And then you, oh, my shoelace kind of came out. So what can we pull out? 3x, right? Leaves us with 3x plus 10 plus another 3x plus 10 still equals 0. Remember that? Factoring by grouping. And then we're going to pull out 3x plus 10, and we're left with another 3x plus the placeholder 1 equals 0. Are you good? Okay. So again, this is a lot of review of what we've done. Factoring, setting things to 0. So we have two linear equations. So 3x equals negative 10, x equals negative 10 thirds, or 3x equals negative 1, x equals negative 1 third. Right? So we're done. So that was a lot of busy work. Another way, any questions on this, by the way? We just kind of worked it out. We opened up the parentheses, we combined like terms, we factored, we got the answer, right? And by the way, again, if you're stuck on factoring, you can always use the quadratic formula, but the quadratic formula will get really huge here, because you'll be squaring 33 at some point, whatever that is. No, I changed. No, this is the 33. I split 33 into 30 and 3, right? And then you factor by grouping. So messy, right? This is not an easy problem. The other way that I can do this, method 2, the substitution method, I can say let u equals, what should u equal to in this case? If I want to substitute to make it look like a quadratic. 3x plus 2, right? That's that common term, 3x plus 2. So if I do that, the whole problem becomes u squared plus 7u minus 8 equals 0, right? Which is a very friendly quadratic that I can solve. This factors into u plus 8 and u minus 1 equals 0, right? Two numbers at C. Factoring became very easy here. So that means if you set them to 0, u plus 8 equals 0, or u minus 1 equals 0. So u equals negative 8, u equals 1, right? Well, it's a happy class. So then we solved our first simple quadratic. Then we're going to substitute back. So u was 3x plus 2, so that means 3x plus 2 equals negative 8. or 3x plus 2 equals 1. These are the two simple linear equations, right? So when you solve them, you subtract 2, divide by 3, x equals negative 10/3. You subtract 2, divide by 3, x equals negative 1/3. So we still end up with the same solutions, right? Which way is easier? Right, it's just because we got, it's a little more advanced technology, but it made your life a lot easier. You're solving simpler problems on the way. We didn't have that nasty factoring, or if you were stuck on factoring, the quadratic formula would have been even worse. Because you have to go 33 squared minus 4 times 9 times 10. So whatever that is, right? Okay. How about this example? X over x plus 1 squared minus 4x over x plus 1 minus 12 equals 0. We can solve this problem straight up, because this is an equation that involves rational expressions. I can solve that by clearing out the denominators. Remember that? Yeah, let's do both, so for the sake of appreciation. Because really what I have right now, it is x squared over, so this is method 1. Method 1, rational equation. Because again, if those parts, the x plus 1, were different, then you would have to solve it by rational equation. There's no cute way of doing this problem. So the LCD here is x plus 1 squared, right? That's the LCD. And what we agreed on, and this is a good review, by the way. This is how we solve the equation that involve rationals. We'll multiply both sides by the LCD. So that will kill all little denominators. We'll multiply both sides by the LCD. No, it's plus 1, right? Plus. Right? That's how we did that before. Now look at the fun part. So we're going to start distributing. Distribute the first. The denominators cancel, right? Remember that trick? And we're left with the numerator, x squared. Then we distribute through the second one. Only x plus 1